Dear learners, I welcome you all to this module. The title of the module is Introduction to Linear Transformation and Matrix of a Linear Transformation. In the session, we are going to learn about what we mean by transformations, the domain, codomain, image and range of transformations. Then we discuss about matrix transformations. We proceed our study specifically about linear transformations. Towards the end, we discuss about matrix of a transformation, one-to-one mapping, onto mappings in terms of transformations. Numerous results associated with these topics are also discussed. Here, matrix equation Ax is equal to B is thought of as the matrix A being an object that acts on a vector x by multiplication to produce a new vector called Ax. Now, solving the equation Ax is equal to B is equivalent to finding all vectors x in R power 4 or maybe in R power n that are transformed into the vector B in R square under the action of multiplication by A. Now, we are going to see about the transformation, domain, codomain, image and range. A transformation T from R power n to R power m is a rule that assigns to each vector x in R power n a vector T of x in R power m. The set R power n is called the domain of T and R power m is called the codomain of T. The notation T from, that is colon, from R power n to R power m indicates that the domain of T is R power n and the codomain of T is R power m. For x in R power n, the vector T of x in R power m is called the image of x, that is under the action of T. The set of all images T of x is called the range of T. Next, we shall discuss about matrix transformation. Now, we shift our focus to the mappings associated with matrix multiplication. For each x in R power n, T of x is computed as Ax, where A is an m by n matrix. Such a matrix transformations can be denoted by from x to, that is arrow symbol, to Ax. Here the domain of T is R power n when A has n columns and the codomain of T is R power m when each column of A has m entries. The range of T is a set of all linear combinations of the columns of A because each image T of x is of the form Ax. Now, we shall discuss an example. Consider the matrix A is equal to 0 0 0 0 1 0 0 1 0 0 0 1. Then the transformation from x to Ax projects points in R cube, that is R power 3, onto the x to x3 plane, because when you project it, x1 x2 x3 will give you 0 0 0 0 1 0 0 0 1 multiplied by x1 x2 x3, that is equivalent to 0 x2 x3. Example 2, the transformation from x to Ax such that A is equal to 1 lambda 0 1, where lambda is a real number, is called a shear transformation parallel to x axis. These types of transformations are widely used in the field of computer graphics. The next example, we have a matrix A that has 1 1 0 1 1 1 as entries, and let T of x is equal to Ax, that is the transformation is equal to Ax, and so T is from R square to R cube is a matrix transformation. If U is equal to the column vector 3 4, then T of U will be equal to T of 3 4, that is nothing but A multiplied by x, right. Here the A is 1 1 0 1 1 1, the vector that we have is 3 4. Therefore, you have 7 4 7 as the answer, that is the column vector as your answer. Then evaluate B such that B is equal to T of V, that is equal to AV. In other words, we want to solve the matrix equation AV is equal to B. That is 1 1 0 1 1 1 is a matrix multiplied by with V vector is equal to 7 4 7. We form an augmented matrix and row reducing gives us 1 1 7 0 1 5 1 1 7, that is again equivalent to a matrix 1 0 2 0 1 5 0 0 0. So, this gives us a solution that x is equal to 2 and y is equal to 5. So, there exists a unique solution v is equal to 2 5. Next, we shall discuss about linear transformations. A transformation, we can call that as a mapping also. We used to denote that by T is linear if it satisfies the two conditions. First condition is T of u plus v is equal to T of u plus T of v for all uv in the domain of T. Next one is T of cu is equal to C multiplied by T of u for all u and for all scalars C. Next we shall see a proposition. If T is a linear transformation, meaning that it has to satisfy the above two conditions that we have mentioned, then T of 0 is always 0 and T of cu plus dv is equal to C multiplied by T of u plus d multiplied by T of v for all vectors uv in the domain of T and for all scalars C and d. We shall prove. First one is we have to prove T of 0 is equal to 0. It follows from the second result that we have mentioned above, because T of 0 is equal to T of 0 u, as 0 can be written as 0 multiplied by u, and that is equal to 0 multiplied by T of u, that is again 0. So, that we proved that T of 0 is equal to 0, and then we claim T of cu plus dv is equal to C multiplied by T of u plus d multiplied by T of v. Applying both the results, we will get T of cu plus dv is equal to T of cu plus T of dv, because of the fact it has to satisfy the two conditions. Applying the first condition, we are getting this one, and then again you can take C outside and write this is equal to C of Tu plus d multiplied by T of u, again from the linear transformation property. So, we are able to prove T of cu plus dv is equal to C multiplied by T of u plus d multiplied by T of v. Now, the result can be extended by multiple applications to derive the result. T of C1 V1 plus C2 V2 plus etc. Cp Vp can be written as C1 multiplied by T of V1 plus C2 multiplied by T of V2 plus etc. plus Cp multiplied by T of Vp. We shall see an example. Given a scalar r and define a transformation T from r square to r square given by T of x is equal to Rx, where T is called as a contraction when r lies between 0 and 1, and it also takes the value 0 and 1, and the dilation when r is greater than 1. Let us take r to be equal to 3, and we are going to show that T is a linear transformation. So, we are going to take two vectors in r square, that is u and v, and let C and D be two scalars. Then consider T of cu plus dv. You can write that as 3 multiplied by cu plus dv according to the transformation that we have defined, and we have taken r to be equal to 3. That will give us the value to be equivalent to 3 multiplied by cu plus 3 multiplied by dv. That is nothing but C multiplied by 3u plus d multiplied by 3v, that is equal to C of Tu, C multiplied by T of u plus d multiplied by T of v by applying the vector arithmetic. Therefore, T is a linear transformation. Next, we shall see another example. We are going to define a linear transformation from r square to r square defined by T of x is equal to 1 1 0 1, the matrix, multiplied by x1 x2, that is x1 x2 and x2 as a column matrix. That is how we are going to define my T. Then the images under T of u and v vector, that is if u is equal to 1 and 2 column vector, v is equal to 3 minus 1 and u plus v will be equal to 4 and 1. The images are T of u is equal to 3 2 and T of v is equal to 2 minus 1, T of u plus v is equal to 5 1 according to the operation that we have defined already. We can verify the property of linear transformation, that is T of u plus v is equal to T of u plus T of v for all u and v in the domain of T, since here the column vector 5 1 can be written as a linear combination of 2 minus 1 plus 3 2. The matrix of a linear transformation, the remaining part of the session shows that every linear transformation from r power n to r power m is actually a matrix transformation from x to Ax, and that important properties of T are closely related to known properties of the matrix A. The key to identifying A is to observe that T is completely determined by what it does to the columns of the n by n identity matrix In. For example, if you consider the columns of I2, that is 1 0 0 1, or that is E1 is equal to 1 0 and E2 is equal to 0 1, we are considering the columns alone. Suppose T is a linear transformation from r square to r cube, and defined by T of E1 is equal to 5 minus 7 2 as a column vector, and T of E2 is equal to minus 3 8 0 and again as a column vector. With these information, we intend to find a formula for the image of an arbitrary x in odd power 2. Consider this x to be equivalent to x1 x2. That can be written as x1 multiplied by 1 0 plus x2 multiplied by 0 1, and this 1 0 can be written as E1 and 0 1 can be written as E2. Therefore, we have T of x to be equivalent to x1 E1 plus x2 E2, and again we have already proved that T of 0 is equal to 0, that is for identity also, vectors, column vectors also. Therefore, we have T of x is equal to x1 T of E1 plus x2 T of E2. That is, we have x1 multiplied by the column vector 5 minus 7 2 plus x2 multiplied by the column vector minus 3 8 0. That will give us 5 x1 minus 3 x2 minus 7 x1 plus 8 x2, 2 x1 plus 0 and again is the column vector. Let us see a theorem on linear transformation now. So, here this theorem states we have a linear transformation that has been defined from R power n to R power m. Then there exists a unique matrix A such that T of x is equal to Ax for all x in R power m, where this A is a m by n matrix and jth column of A is denoted by T of Ej, where Ej is equal to 0 0 0 1, that is in jth place I have 1 0 0, and this A is nothing but T of E1, T of E2 etc. T of En, and T of Ei's are all the column vectors of A. So, that is what we are going to prove. I will repeat the statement for your better understanding. So, we have a linear transformation corresponding to the linear transformation. We have to prove that there exists a unique matrix Ax, and with respect to or satisfying these properties. So, now we shall try to prove this. Consider x in R power n. So, if x you are taking from R power n, then it is a vector. You can consider that as a vector consisting of n components x1, x2 etc. xn. So, you have x and you can write that as Inx, where In is the identity matrix of n by n order. So, now this In can be written as E1, E2 etc. En multiplied by 1x. You have x1 E1 plus x2 E2 plus etc. plus xn En. So, this is your x. Then what about T of x? T of x is nothing but T of x1 E1 plus x2 E2 plus etc. plus xn En. So, now according to the properties of linear transformation, this can be written as x1 T of E1 plus x2 T of E2 plus etc. plus xn T of En. That is nothing but T of E1, T of E2 etc. T of En multiplied by x1, x2 etc. xn, and this you can write as Ax. So, you have T of x to be equivalent to Ax. For the existence, define another transformation, and existence and uniqueness, define another transformation R power n to R power m defined by T of x is equal to Bx. So, therefore, here you have T of Ej to be equal to Bij, that is equal to Bj, and here your A is nothing but your B, that is equivalent to B1, B2 etc. Bn, that is A is nothing but the column vector B1, B2 etc. Bn, that is nothing but B. So, we are able to prove the uniqueness of the matrix A and the existence of it satisfying these properties. So, next we shall see an example now. We are going to evaluate T of x is equal to 7x, where x is in R power 2 R square. So, now since we are talking about R power 2, it is enough if you talk about E1 and E2. E1 is nothing but column vector having 1 in the first place, and E2 is again a column matrix having 1 in the second place. So, now you have T of E1 to be equal to 7 E1, that is 7 0, and T of E2 is equal to 7 E2, that is equal to 0 7. So, what you have to do is you have to combine the columns and write. So, it is not like doing any operation, this is like combining. The first column you have to write in the first and the second column you have to write in the second. So, just like we have seen in the previous theorem stating that A can be written as T of E1, T of E2, etc. T of Ej and etc. T of En. So, this is first one T of E1 is the corresponds to the first column of A, and T of E2 corresponds to the second column of A. Therefore, what I am doing, I am writing 7 0 and 0 7. So, this is your corresponding matrix A. Therefore, corresponding to this linear transformation, I am able to get a matrix A 7 0 0 7 satisfying the conditions mentioned in the theorem that we have seen. Now, we shall see another theorem that says T is a linear transformation from R power n to R power m, then T is a 1 function if and only if T of x is equal to 0 has a trivial solution. Now, so now we have to prove this. So, first T of 0 is equal to 0. So, this we have already proved while we are seeing the definition of linear transformation. As soon as we finish that, we prove T of 0 is equal to 0. Therefore, this is always true. Since T is a linear transformation, we always have T of 0 to be equal to 0. So, do not have to worry about that. Now, what you have to do is, you have to take T is 1 and you have to prove T of x is equal to 0 is a trivial solution. And if for the converse part, what I am going to do is, I am going to prove in a contradiction way. That is, if T is not 1 and I am going to prove T of u is equal to this does not have any trivial solution. So, now you can assume that this has a unique solution. So, now T of 0 is equal to 0 we have already seen. So, now if T is 1 then T of x is equal to 0 is a trivial solution, and it is a unique solution because the mapping is said to be 1 if each b in R power n is the image of at most one x in R power n. Therefore, equivalently, if T is 1 we can say this one, right. The second one is, if T is not 1 then what happens if T is not 1 there exists some b for which two images or two elements are mapped, or two elements will give you the element b. Therefore, there exists u and b where u and v is not equal to one another, and getting T of u is equal to b and T of v is also b. Therefore, if you consider T of u minus v according to the property of linear transformation, this can be written as T of u minus T of v. What is the value of T of u? The value of T of u is b. The value of T of v is also b. B minus b, we are getting 0. Therefore, T of u minus v is equal to 0. Now, here this happens only if u minus v is equal to 0 and we are getting u is equal to v. But in the starting we have assumed u is not equal to v because T is not 1 we will be able to find two different v's such that T of u is equal to b and T of v is equal to b. Therefore, now you have these two are equal, this is contradiction to one another. Therefore, our T that we have considered, that is not 1 that assumption is wrong. Therefore, from here we can say T of x is equal to 0 has more than one solution, meaning that if T of x has a unique trivial solution, then T should be 1 and if T should be 1 then T of x has a unique trivial solution. So, from the previous theorem we have proved that it has if it is 1 it has T of x is equal to 0 to be the only one solution, that is trivial. If T of x is equal to 0 that has a only one trivial solution, then T is 1 we proved that by first by taking T is 1 and next by taking T is not 1. Now, we are moving on to the next theorem, and we have T to be a linear transformation from R power n to R power m. And first statement, if T is onto, if and only if the columns of A spans R power m. Next one, if T is 1 then the columns are linearly independent. Okay, for the first statement, if the column spans R power m, that is possible if and only if Ax is equal to b is consistent. That is, T of x is equal to b. Corresponding to A, we have a transformation, right? That T of x is equal to b has a solution. That is, while considering T, we are finding the matrix, only then we are proceeding to here. Therefore, T of x is equal to b has a solution. This is true if and only if our T is onto. Therefore, we are able to prove columns spans R power m, then T is onto, and if T is onto, then the column spans R power n. The next part is we have to prove T is 1 1 if and only if the columns are linearly independent. So, if T is 1 1, then according to the previous theorem, T of x is equal to that is T of 0 is equal to 0 has is the only trivial solution. Now, if T of x is equal to 0 and Ax is equal to 0, then T is 1 1 if and only if this Ax equal to 0 has only the trivial solution. This will happen only if the columns of A are linearly independent. Therefore, we are able to prove when T is 1 1, then the columns of are linearly independent and the vice versa also. We shall see an example now. So, consider the linear transformation T of x1 x2 that is defined as 3x1 plus x2 comma 5x1 plus 7x2 and x1 plus 3x2. So, here the T of x value is nothing but 3x1 plus x2, 5x1 plus 7x2, x1 plus 3x2, and this can be put in the form of 3 1 5 7 1 3 and x1 x2. So, you can see here this is a 3 by 2 matrix. Therefore, our transformation is defined from r square to r cube. You can see it here, we started with 2 and it takes 2 images to r power 3. So, corresponding to this the matrix A is 3 1 5 7 1 3, that is corresponding to this linear transformation. We have the matrix A to be 3 1 5 7 1 3. So, we have started from a linear transformation that has been defined on r square and we defined in this way. From the question itself you can see it here, it takes only the 2 inputs, that is r square, and gives us the 3 components in the output. Therefore, which means that it is defined in r cube and it is defined on r2, it takes the value 2 r3 and the corresponding matrix will be of the order 3 by 2 and the matrix is 3 1 5 7 1 3. Dear learners, we are at the end of the session. In this session, we learnt about transformations, particularly linear transformation, the domain, codomain, image and range of transformations. Then we discussed about matrix transformation. We proceeded our study specifically about linear transformation starting from transformations. Towards the end, we discussed about matrix of transformation, one-to-one mapping, onto mappings in terms of transformations. Numerous results associated with these topics were also discussed with suitable examples. Dear learners, I hope this module will be useful to you. We will see you again in the next module. Thank you.